boys and girls, we're going to watch a brain pop together to review the two laws of motion that we talked about last week and also to introduce Newton's third law of motion. Remember, the first law is an object in motion remains in motion, an object at rest remains at rest until a force is applied. Remember that first law is also inertia. Inertia is the tendency to keep doing what you're already doing. So when you say that an object in motion stays in motion, that's literally an object continuing to do what it's already doing. Newton's second law is all about force and mass and acceleration. Something with more mass requires more force in order to accelerate, and something with less mass requires less force in order to accelerate. The tricky part of that is that accelerating is not just getting faster like we usually think. Accelerating can be getting faster, getting slower, speeding up, what else can it be? Starting, stopping, changing directions. Because acceleration is a change in velocity, which is a change in either speed or direction. And without saying more, let's go ahead and start watching the brain pop. I'll stop as needed throughout the video.
Thanks, Moby. Hey, Tim and Moby. Can you tell me about Isaac Newton's 3 laws? From Jerome. Well, Isaac Newton was a scientist who lived in the 17th century. We have a whole movie about him, so you should check it out. Anyway, Newton came up with the 3 laws of motion that can be used to explain how and why stuff moves. Well, yeah, these laws are still in use today, so I'd say he was pretty smart. Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless an unbalanced force acts on it. You probably don't think about it this way, but when a car is moving, everything in it and on it is moving along at the same speed. If the car has to stop suddenly, the objects in and on the car will continue moving forward. Guess we should have tied those on tighter.
Right. So let's just think about what just happened. When he slowed down because of the object flying in the air, he applied force to the brakes on the car, which was just like in our exploration last week, where you apply force only to the note card and not to the penny. So the note card moved, but the penny stayed where it was until gravity pulled it down. It's the same idea as when I pulled the tablecloth out. I was only pulling the tablecloth, right? And not applying force to the matter that was on the table. So the heavier plate and cup stayed there. In this video, the brakes stopped the car or slowed the car, but there was no force applied to the skis on top, so the skis go flying. And we talked about last week the same idea that if you're in the car, you are not having any force applied to you from the brakes. So you keep moving when the car stops, which is why people hit the windshield and hurt their necks and that sort of thing during a car accident.
An object's forward motion will continue until an unbalanced force acts in the opposite direction to stop it. So, our seatbelts provided the unbalanced force that stopped our bodies from moving forward. But those ropes didn't provide enough force to balance out the ski's forward motion. Why didn't it keep going? Well, in this case, the force acting on the rock was friction. Friction is the resistance caused by any two objects in contact, and it always acts in the opposite direction of the motion. Newton's second law says an object that has an unbalanced force acting on it will accelerate in the direction of that force. When you're just sitting there, two forces are acting on you all the time. Right now, gravity is pulling our mass toward the center of the Earth, and the upward normal force of the ground is pushing up against gravity. We could sit here all day and go nowhere because these two forces cancel out. This hill...
That's what they mean by balanced forces, when the amount of force cancels each other out and there's no motion. And this is Newton's first law too. The object at rest will stay at rest until there's some other force.
Is a different story. At this angle, gravity and the normal force are not canceling each other out. Gravity wins, and we accelerate. The net force that's acting on us and making us accelerate is a combination of the normal force and gravity. Look, friction. Newton's third law is this: force.
Okay, now keep in mind, he made the joke at the end that friction was what stopped him, but that's literally the truth. And you could also hear the sound of the sled rubbing up against the snow the whole time. So friction was also acting on the sled in order to slow it down, which is why if you were designing a sled, you would design it with a really smooth bottom. So hopefully you would go really, really fast on the hill and on the ice.
Forces always occur in equal and opposite pairs.
All right, now here's Newton's third law. For every action, there's an equal, get that, equal sign, and opposite reaction. So every time you do something and apply a force, there's a reaction to it, whether you realize it or not.
When I pushed that door, it pushed right back at me with equal force. The door was the one that moved because friction between my feet and the floor combined my mass with the building's mass. The door is on hinges which decrease friction, so it accelerates open. Maybe if you took off your roller skates. Or not. Oops. Well, that's about it for Isaac Newton's laws of motion. I'm gonna get Moby an ice pack.
All right, so we're going to stop there and I'll bring you something else so we can start to talk about Newton's third law. Now, Newton's third law is not a huge thing in fifth grade science. The second law is the one that we really study the most about force and mass and acceleration, but I just think it's kind of silly to teach you about inertia and to teach you about force and mass and acceleration and not even mention the third law. So we're going to spend a little bit more time on that today.